Welcome to another physics class. Today we want to continue from our topic, simple harmonic motion. And what we treated in the last lesson is example to illustrate simple harmonic motion. The first example is a simple pendulum performing simple harmonic motion. So, and I promise today we are going to the example 2, under which we want to look at a loaded spiral spring oscillating up and down. And don't forget, under each example, we were looking at 1, restoring force, F. 2, the acceleration of each, acceleration of simple harmonic motion under each system. 3, angular frequency. This is omega, this is A. And the next one, which is number 4, is period. Period of simple harmonic motion under each example. That is T. Next is velocity. Velocity of simple harmonic motion. And the last one is, which is number 6, is energy. Energy in simple harmonic motion under each system. So today we want to look at a loaded spiral spring oscillating up and down, as I said. And don't forget to join this class, because I've taken this class as a progressive one. So if you want to join the class with the maximum things, please try to like, share, and subscribe. So when I post a new video or upload a new video like this, you'll be able to get the notification in time. Now, from the diagram on the board, we want to use this one to explain a loaded spiral spring. This is a spiral spring in which load is on, and this is the original position of this spiral spring. When the load is hung on it and displaced a little, we have it like this. On releasing the spiral spring to oscillate up and down, then we are going to have it in these 3 cases. So from here now, the displacement here, from here, let's call it x. And the maximum displacement, which is amplitude, that is from this place to this place, let's call it A. And from here to here, as I said, let's call it S, which is displacement. So from here to here now, don't forget, we want to combine this one with what we learned under Hooke's law. Now say from Hooke's law, that is, Hooke's law state that provided that the elastic limit of an elastic material is not exceeded, the force applied is directly proportional to extension. But we are not dealing with extension now, we are dealing with amplitude and displacement. So we can now say from that statement, our F is equal to KE. And since we said this is extension now, we now say this one to S as displacement. Now, since we want to look at the first thing under this one, which is restoring force. Now, the restoring force F will be equal to minus KS. Why is it minus? Because by the time you displace this thing and you allow it to move up and down, don't forget we said in the last lesson that restoring force is the force that will restore this spiral spring to its original position or equilibrium position. So that is why the restoring force usually take negative action. It restores the system to its original position. So that is why F is equal to minus Ks. Now, since we said the restoring force is equal to F is equal to minus Ks, then the next thing we are going to consider is the accelerating force. That is the force that will accelerate this thing. So accelerating force now. Accelerating force. That one is normally F is equal to ma. That is why we call it accelerating force. Now, since this one is F, this one also is F, call this one equation 1, call this one equation 2. If we equate the two together now, let's say equating 2 to 1. So we are going to have ma will be equal to minus Ks. Then the acceleration of a spiral spring will now be equal to A is equal to minus Ks over M. That's the acceleration of a spiral spring. Acceleration of a spiral spring under simple harmonic motion. Now, from what is on the board now, don't forget we said this one is acceleration of a spiral spring under simple harmonic motion. Don't forget this our A, but A from general formula of simple harmonic motion, which we have done before, is equal to minus omega square S. Don't forget our S, where S is displacement. That is displacement from the equilibrium position. And A also is minus because don't forget the definition of acceleration of simple harmonic motion, that is always directed toward the fixed point or toward an equilibrium position. That is why it always takes minus sign. So since A is equal to this one, and from general formula A is equal to this one, let's equate the two together. So we are going to have minus omega square S will be equal to minus Ks over M. So minus will cancel minus and S will cancel S. So we are going to have omega square will be equal to K over M. Therefore, the angular speed or angular velocity of a loaded spiral spring will be equal to square root of K over M. Why this one is angular frequency, call it angular frequency or speed, or you call it angular velocity of a loaded spiral spring performing simple harmonic motion. What is the value of K now? Where K from Oak's law is equal to force constant. Force constant, or you call it elastic constant or elastic constant. Force constant or elastic constant. So that is the angular frequency of a loaded spiral spring performing simple harmonic motion. Next, from here, we can now get the period of a spiral spring under simple harmonic motion. Now, period. Now, already we know that the symbol for period is capital T. And from general formula of simple harmonic motion, we have period is equal to 2 pi over omega. 2 pi over omega, that's from general formula. Now, mind you, the omega or the angular frequency of a loaded spiral spring has already been be calculated. So we can now substitute root k over n for omega. So we are going to have t now will now be equal to 2 pi divided by root k over m. So from here now, our t now will be equal to 2 pi root m over k. That is the period of a loaded spiral spring performing simple harmonic motion. So this is the period of a loaded spiral spring under SHL. If you are with me, during our last lesson, when we are dealing with that of the suspended simple pendulum, you notice that the period of a suspended simple pendulum is totally different from this one. That period of a suspended simple pendulum is t on its own is equal to 2 pi root L over G. That is for suspended simple pendulum. So when you are now given calculation, depending on the system used, you now determine the formula you are going to apply. If you are given under spiral spring, then you apply all this one. If it is under simple pendulum, you apply what we've done in the last lesson. We said the period T for a loaded spiral spring is equal to 2 pi into square root of m over k. That's the period. Now, from what we have written on the board now, if we carry both sides, we are going to have t squared is equal to 4 pi square in m over k. So this one will now give us t squared is equal to 4 pi square over k into m. Now, from what we are looking at now, if a graph of on graph, if a graph of t square is plot against m, then we are going to have the slope of the graph as the slope of the graph will be equal to s, which is equal to 4 pi square over k. So when you get the value of the slope of the graph, then it now be equal to 4 pi square over k, where this k is force constant. Then from there we can now calculate the force constant of the spring. Sk now is equal to 4 pi square. So k now will be equal to 4 pi square over s. So this one will give us the force constant of that spiral spring used to demonstrate the experiment. And as I said, the graph of t square, that is second square, will give us, if we start both axes from origin 0, 0, according to the equation, we are going to have, this one is versus m, so we are going to have a straight line graph. And once it is a straight line graph, the slope, according to what we have said, s will be equal to 4 pi square over k. So the slope of this t square again m will give us the value of the 4 pi square over k, and from there we can now calculate k as we said here. Now, from this point now, that is from this point, since we said 4 pi square over k is a constant, so we can now say t square is directly proportional to m. where t squared now will be equal to km. K now will be equal to what? T squared over m. Now, depending on number of times now that the experiment is being performed, then we can now have k will be equal to k t squared 1 over m1, that is mass of the load. Mass of the load hang on this spiral spring now. That will be m1 over t equal to t squared 2 over m2 equal to t squared 3 over m3. Since the mass on this spiral spring can be varied, so we can have series of value like this. The next thing we are going to consider under this loaded spiral spring is the tension T in a loaded spiral spring. Tension T in a loaded spiral spring. When you say tension, when a load is being hung on this spiral spring, there must be vertical force that will pull the load upward to balance the motion. So the vertical force is what you call tension. And the value of this one, tension also is a force. So we can now say T prime, just to differentiate between the period and tension, is equal to F, which is equal to Ks. So the tension also is equal to F is equal to Ks. That is force constant multiplied by the displacement produced by the load on the spiral spring. That's the tension. Now the next thing is velocity. Velocity and energy in a loaded spiral spring. Now, under the velocity now, we need to consider the motion of this loaded spiral spring. We've said from here to here is amplitude, and from here to here is displacement. And when it is moving up and down, that is another case entirely. So to consider this one in terms of energy now, we are going to have from Hooke's law again, or yes, we've said the energy stored in a extended spiral spring is equal to the energy stored energy stored in a loaded spiral spring. That one by then we said is E is equal to half Ke squared. That is from Hooke's law. But as I said the other time, we want to apply the amplitude and displacement instead of E now. Then for this side now, we are going to have the energy here will be equal to half Ka squared. That is for this one. And the energy here will be half K squared. And at this particular point, when it is moving up and down, the energy here will be half half mv squared. That's the kinetic energy of moving it up and down. Under this one, the name given to this one is, we call it elastic potential energy. That's elastic potential energy. Here now, when you extend it, we call this one compressive potential energy. and air. Because we call it, still call it potential energy here, but we just extend and compress this thing. This thing is not yet on motion. So, but here now, the energy here seems to be moving up and down. It is called elastic kinetic energy. From the diagram above now, this one is the total energy. The energy here is total energy. So, and the total energy, according to the conservation of flow energy, will be equal to half Ks square plus half mv square. So from there now, we can now say, coming to this side now, we can now say the total energy E, which is half Ka square, will be equal to half Ks square plus half mv square. Mind you, we are looking for velocity. Let's make this one the subject of the formula. So we are going to have half mv square will be equal to half Ka square minus half Ks square. From there, so we are going to have half mv square then is equal to half and k are common. So half k into a square minus h square. You look at this side, half is common, so half will go away. So we are now left with mv square is equal to k into a square minus s square. Make v the subject of the formula. We are going to have v square is equal to k over m into a square minus s square. Then v now, which is the velocity of a loaded spiral spring, will be equal to square root of k over m into a square minus s square. So that will be the velocity of a loaded spiral spring. But to have maximum velocity now, V maximum, don't forget from the beginning that the maximum velocity of a simple harmonic motion will occur at s is equal to 0 or at the equilibrium position. That is at equilibrium. If that is the case and s is equal to 0 here, we are going to have V maximum for a loaded spiral spring as square root of k over m into a square. So that will be the V maximum of a loaded spiral spring. And finally, we are going to have V maximum of a loaded spiral spring. V maximum is equal to square root of k over m multiplied by a. That is the maximum velocity of a loaded spiral spring. I said an energy. From the explanation, energy had been explained because we said from this place, the total energy is half Ka square. The energy here is half Ks, and the energy here is half mv square. So when we say total energy is equal to this one, we know that majorly the energy stored that we reserve in this one will be kinetic energy. Let's take this one as example 1 under this one. A mass of 0.2 kg suspended at the end of a spiral spring is set into vibration If it takes 34 seconds to complete 20 oscillations, calculate the 1. Period of the oscillation, 2. Force constant, C. Angular speed, D. Acceleration of the spring, if the displacement is 0.1 meter. Now, from the question, the following parameters were given. Mass, F is 0.2 kg. Is 0.2 kg. Then time 34 seconds. The number of oscillation, N, 20 oscillation. What else is given? Then at the bottom of the question, S is given. Displacement 0.1 and pi 3.142. Now, the fourth question says we should calculate period of the oscillation. Mind you, from the general formula of simple harmonic motion, we'll be able to calculate the period of this spring, because the second question says we should calculate the force constant, and we have mass, time, number of oscillation. So to calculate the period now, 1 period T, that one will now be equal to the time taken over number of oscillation from the general formula. The time taken according to the question is 34. Number of oscillation is 20. So this one will now give us, and the answer to this one, as I said, will be 1.7 seconds. Question B part of the question now. B part asks us to calculate the force constant, K. Now, the force constant, we were not given F. If F is given, then we now say F is equal to Ks. But force is not given. So the better formula to calculate, since we know the period, is T is equal to 2 pi into square root of M over K. That's the correct formula. Now, from this formula now, mass is known. We've calculated capital T. So let's make K the subject of the formula. So this one will now give us square root both sides. That is, square root both sides, we are going to have 4 pi square into M over K. So this one will now give us T square K is equal to 4 pi square M. So K now is equal to 4 pi square M over T square. So from there, put in all the value now. K now will be equal to 4 multiplied by 3.142 all into square multiplied by mass 0.2 divided by 1.7 square. The answer to this one, K, will now be equal to 7.8977 divided by 1.7 square, that's 2.89. Now the final answer for K will be 2.73 Newton per meter. That is for force constant. The next question is angular speed. That's question number C, angular speed. See now, angular speed equal to square root of K over M. And from what we've calculated, our K is 2.73, then over M. Our M is 0.2. then square root 2.73 divided by 0.2. Now, that will be 13.65. Square root 13.65. An angular frequency of velocity, as we said from the question, will be equal to 3.694 rad per second. Now, the next one, which is question D, is acceleration, which is equal to minus ks over m. Mind you, the negative sign there just indicate the direction. So it will be the value for k, according to what we calculated, is 2.73. Our s from the question is 0.1. The m is 0.2. So a will be equal to, now a will be equal to 0.273, then divided by 0.2. So the answer with A will now give us 1.365 acceleration. That is meter per second square. Now that's the end of the question. You calculated everything. Now let's take this one as example 2. A mass of 0.1 kg on a spiral spring oscillating SSM with amplitude of 0.2 meter and a period of 2.8 seconds. Calculate the A, force constant of the spring, B, maximum PE of the mass, and C, potential energy if the mass is 0.12 from the equilibrium position, pi 3.142. Now, let's write out the parameter as given in the question. M is 0.1 kg, amplitude, that is 0.2 meter, period, t 2.8 seconds. And to calculate C, we are given is 0.1 as 2 as a displacement, 0.12 as displacement, then pi as 3.142. A now, force constant, that is K, and the first formula is T is equal to 2 pi into square root of M over K. We need K, make K the subject. So taking the square of both sides, T squared will be equal to 4 pi squared M over K. T squared K is equal to 4 pi squared. K now is equal to 4 pi squared M, then over T squared. Now, put in the value, we have K is equal to 4 multiplied by 3.142 square multiplied by mass, that is 0.1, then divided by period, that is 2.8. Now this one, 4 multiplied by 3.142 square multiplied by 0.1 will give us 3.9488, then over 7.84. Now the answer is 0.5036. And what's the unit? Newton per meter. That is the value of force constant. Then B part of the question say we should calculate. B part of the question say we should calculate maximum PE, that is PE maximum will be equal to half KE squared. and our K can be calculated. That will be half multiplied by 0.5036, and our A on the board is 0.2 square. This one will now give us the maximum PE will be equal to 0.5036 multiplied by 0.04 all divided by 2. Maximum PE maximum will be equal to 0.0101 joule. The last question under is PE if the mass is 0.12 meter from the equilibrium, that is x. So question C, PE at that point at 0.12 meter. That one will now give us PE will be equal to half Ks squared. So that one will now give us half multiplied by our K 0.5036, our S is 0.12 square. This one will now give us 0.5036 multiplied by 0.0144, then divided by 2. So PE at that point will be equal to, now the P is equal to 0.003626 joule. That's the final answer to that question. Now let's take this one as example 3. The mass of 200 grams on a spring under SSM with an amplitude of 0.2 meter. The maximum force acting on the mass is 0.064 Newton. Calculate the 1. Maximum velocity of the spring. B. Period of oscillation of the spring. Let's write out the parameter in the question. Mass is given as 200 grams. Amplitude A is given as 0.2 meter. Force is given as 0.064 Newton. And we have to calculate maximum velocity. The first thing we are going to do, amplitude is a meter, force is a Newton, but mass is given is gram. To be correlated, we need to convert this one to kg. So we divide this one by 1,000. 200 divided by 1,000. That one will now give us 0.2 kg. That will be mass in kg. Now, to continue, we have to calculate maximum velocity. A, maximum velocity. Don't forget from our formula, V maximum for a loaded spiral spring will equal to square root of K over M multiplied by amplitude. And from the question, K is not given, but mass is given, amplitude is given, force is given. And don't forget, we know that our but F is equal to Ka. F is equal to Ka, that is from Hooke's law, because the amplitude is given. Then we can now say K will be equal to F over A. Then that one will now be equal to, our F given is 0.064, then divided by 0.2 as amplitude. So K now will be equal to, K will be equal to 0.329 Newton per meter. Now, since K is given, is calculated now, we can now say V maximum will be equal to square root of 0.32 over 0.2, then multiplied by amplitude, which is 0.2. Will be square root of 1.6 multiplied by 0.2. That will be equal to 1.2649 multiplied by 0.2. So V maximum, that will be 0.25298 meter per seconds. The big question is period. Period T, that is 2 pi into square root of m over k. So this one will now give us T now equal to 2 multiplied by 3.142. Square root of m is 0.2. Then k is, the value of k we got is 0.32. This one will now give us 6.284 multiplied by square root of, that will be 0.625. 0.625. That will be 6.284 multiplied by 0.7905. So the period now will be equal to 4.967 seconds. Let's take this one as example 4. A mass M 0.30 kg is attached to a spring of force constant K, 30 Newton per meter, performing SHM of frequency F 1 over 2 pi into square root of K, has a maximum displacement of 0.015 meter. A. Explain the physical significance of root K over M. B. Calculate the kinetic energy of the system. B2. Tension on the spring. Pi is equal to 3.142. So according to this question, let's write out the parameter first. M is given 0.30 kg. K is given as 30 Newton per meter, and pi is given, according to the question, pi is given as 3.142. Now, the first question, A, has us to explain this physical significance of this root K over M from F is equal to 1 over 2 pi into root K over M. Then the question is, what is the physical significance of that root K over M? And from the series of formula that we have written, we know that omega is equal to root K over M. Therefore, the explanation of this one is that root K over M is equal to angular frequency, or you call it angular speed or angular velocity. That is the physical significance of that square root of root K over M in this question. Then B part of the question. B1 says we should find the kinetic energy of the system. And we know that B1 KE is equal to half mv squared. But to calculate KE, according to this question, V is not given. So we know that the maximum, since the question says the maximum displacement, therefore the maximum speed of a spiral spring will be equal to square root of A over M multiplied by A, that is amplitude, which is given as maximum displacement. If that is the case, then we are going to have square root of our K as given as 30, our M is given as 0.3, then A is given as, according to the question, the amplitude is 0.015. A is given as 0.015, that multiplied by 0.015. V maximum will be equal to root 100 multiplied by 0.015, which is equal to 10 multiplied by 0.015. Maximum will be equal to 0.1. V maximum will be equal to 0.15. 0.15 meter per seconds. If V maximum is equal to 0.15, therefore kinetic energy is equal to half multiplied by 0.30 multiplied by 0.15 square, because the formula is half mv squared, and we calculated V. It will be 0.30 multiplied by 0.0225, then divided by 2. Now, kinetic energy K will be equal to, that will be 0.003375. That is joule, or it will be, that's 3.375 times 10 raised to power minus 3 joule. B part of the question, tension, B2, that will be tension, that is T prime, will be equal to Ka, and our K is already on the board. That will be 30 multiplied by A is 0.015. 30 multiplied by 0.015. Now the tension T prime is equal to 0.45 Newton. Now, let's stop on this example 4 under the second example to demonstrate or to illustrate simple harmonic motion, which is a loaded spiral spring oscillating up and down under simple harmonic motion. And if you compare this one with what we have done before now, under the first illustration, which is under simple pendulum, you could now say that the formula given in each system is different. So when you are now given calculation, you need to be sure of the formula you are going to use. That is the essence of being separating this topic like this. And if you still have question under this one, you are free to ask your question under the link under this channel. And as I said earlier, if you are just joining us under this platform or on this lesson, please, for you to have maximum understanding of what we are doing here, you need to go back and watch our former video on this topic step by step, so that by the time you are having question on any question, you will be able to solve it conveniently. Thank you very much.